Scientists often enter the study of interstellar objects with a sense of uncertainty, and that uncertainty is even greater when an object is only the third confirmed visitor from beyond our solar system in all of human history. The object named 3I/Atlas, detected rushing toward the Sun in early July, immediately attracted global scientific interest. Researchers expected mystery, but the more they observed the object, the more puzzled they became. What began as a routine classification of what seemed like a normal interstellar comet quickly transformed into a fascinating scientific puzzle layered with unusual features and strange behaviors. As powerful instruments focused their attention, NASA's Hubble Space Telescope, the SPHERE-X mission, the Transiting Exoplanet Survey satellite tests, and the James Webb Space Telescope, the findings began to reveal that 3I/Atlas does not behave like any known comet we have studied, whether local or interstellar. Each telescope contributed a different piece of the puzzle, and together they painted a picture of something deeply unexpected, possibly hinting at conditions or processes that do not exist in our solar system. One of the most surprising discoveries came from the combination of SPHERE-X and the James Webb Space Telescope. Their observations revealed that the coma of 3I/Atlas, the cloud-like envelope of gas and dust surrounding the nucleus, contains an abnormally high amount of carbon dioxide. Nearly all comets release a mix of water vapor, carbon dioxide, carbon monoxide, and other volatile materials when they approach the Sun, but the ratios are typically well understood and predictable, based on decades of comet studies. In 3I/Atlas, however, the proportion of carbon dioxide compared to water is the highest ever recorded in any comet-like object. This anomaly raises significant questions about where the object formed, what temperatures it was exposed to, and what kind of radiation environment it experienced before leaving its home star system. Such an extreme chemical ratio suggests that 3I/Atlas may have formed in a region far richer in carbon dioxide ice than the environments that shaped comets in the Sun's protoplanetary disk. Tests provided another surprising piece of information. Although the object was officially discovered in July, researchers looking through archived test data realized the spacecraft had actually captured it months earlier. Even at 6 astronomical units away from the Sun, well beyond Jupiter's orbit, 3I/Atlas was already active and bright. Most comets begin to activate and release gases only when they get much closer to the Sun, where heat begins to sublimate their ices. Activity at such an extreme distance is highly unusual, especially for an object that is not enormous in size. This implies either that the object contains highly volatile materials that sublimate at extremely low temperatures, or that some internal process is driving early activation. The fact that tests captured the object before anyone was even aware of it adds an intriguing historical footnote, showing how much hidden information may exist in the massive archives of modern telescope missions. NASA's Hubble Space Telescope contributed equally surprising imagery. It revealed a teardrop-shaped shroud of dust streaming off the comet's nucleus. This dust is typical of comets, but what is not typical is the absence of a clear, defined tail. Comets almost always display a tail, created when solar radiation pushes dust or gas away from the nucleus, forming a long, characteristic streak in space. However, 3I/Atlas appears to have a muted or nearly non-existent tail. Avi Loeb, a Harvard astronomer well known for suggesting bold hypotheses, commented that this strange configuration might point to unusual physical processes. He even whimsically suggested that an extraterrestrial civilization could have sent the object, although such speculations are not supported by any evidence at the moment. Still, his comments highlight the extent of the object's oddities and how dramatically it differs from both interstellar objects previously detected and comets native to our solar system. Researchers are also deeply interested in the object's origins. In a preprint study, an international team proposed that 3I/Atlas may contain ices that were exposed to far more radiation than comets in our solar system, possibly because the object spent significant time in regions of its host star system subjected to intense cosmic rays or ultraviolet radiation. Another possibility is that it formed near the carbon dioxide ice line, a region in a protoplanetary disk where carbon dioxide freezes out of the gas phase and becomes solid. The exact position of such ice lines differs from star system to star system depending on temperature, star type, and disk composition. If 3I/Atlas formed near this line, it could naturally contain far more carbon dioxide ice than comets formed in our solar system. Such a chemical fingerprint could offer astronomers rare insight into the diversity of protoplanetary environments throughout the galaxy. Although scientists have gathered an impressive set of observations in a short time, they remain cautious. Much of the current analysis is still preliminary and awaits peer review. As 3I/Atlas travels inward toward the Sun and eventually back out into interstellar space, there may be only a brief window left to gather additional data. Every new observation could help refine our models of interstellar objects, which remain some of the least understood bodies in astronomy. With only 2 previous interstellar visitors, Oumuamua in 2017 and Comet Borisov in 2019, researchers have an extremely limited sample size. Each new object is therefore a precious opportunity to deepen our understanding of how materials and planetary systems form throughout the galaxy. Before leaving the solar system, 3I/Atlas will pass relatively close to several major planets. The object is expected to make notable flybys of Jupiter, Mars, and Venus. Loeb has suggested that NASA's Mars Reconnaissance Orbiter could capture close-up observations as the object approaches within less than 2 million miles of Mars. This is an unusually close distance on cosmic scales, providing a rare chance for a spacecraft to view an interstellar object from a vantage point far better than Earth-based telescopes can achieve. If such observations were attempted, they could reveal details about the nucleus of the object, its surface texture, or even the pattern of dust emission. Even more promising is the possibility that NASA's Juno spacecraft, which orbits Jupiter, may be able to intercept the object roughly 5 months after its Mars encounter. Juno carries instruments that could potentially capture data on the composition, mass, magnetism, or radiation environment around 3I/Atlas. A dedicated observational campaign by Juno would not only help solve many of the mysteries surrounding 3I/Atlas, but could also set a precedent for future interstellar object intercept missions. Some scientists hope that eventually space agencies will send rapid response probes specifically designed to chase down these rare visitors. Ultimately, 3I/Atlas is turning out to be far more than just another comet. It is a messenger from another star system, carrying with it the chemical fingerprints and environmental history of a world we cannot yet see. Its unusual carbon dioxide composition, early activity far from the Sun, lack of a traditional cometary tail, and peculiar dust structures all suggest that it is the product of conditions unlike those found in our solar neighborhood. As it continues its brief journey through our system before vanishing back into the darkness of interstellar space, scientists will continue gathering every bit of data they can. The insights gleaned from this mysterious visitor may transform our understanding of how planetary systems form and evolve in the galaxy, offering clues not only about distant stars, but perhaps also about the early history of our own solar system. The more we study it, the more it becomes clear that objects like 3I/Atlas hold secrets that could take decades to fully unravel, making each observation a critical piece of a cosmic story that stretches far beyond the boundaries of the Sun's influence.